We know why rotational spectra now are evenly spaced, why the lines are evenly spaced. But the next question was, why do they go up and down like that? Why are the intensities at very low wave numbers small? They rise to some maximum, and then they dwindle again. So that's a very, very characteristic shape of these bands. But why do they look like that? And in order to answer that question, we have to answer this question of which states are occupied. And what I mean by that is, let's say there's a molecule with a certain vibrational energy, as an example. So we have some E vibrational energy. It's equal to nu E times V plus a half. And if that molecule is not vibrating, which as we'll see is in a second is typically true, then what we say is the V equals 0 state is occupied, or V equals 0 is occupied, or we could use a bracket around 0, and we say that is occupied. We identify a specific state by a specific quantum number, and if that molecule is doing or not doing that thing, which in this case is vibrating, with a certain quantum number in the vibrational motion, then we say that state is occupied or not occupied. So if it is vibrating with V equals 1, then V equals 1 would be occupied. It would be vibrating a little bit. If it's in V equals 0, then it's not vibrating at all, and it just has that 0-point displacement kind of blobbing out character that all quantum objects that are confined have, but it is otherwise not really vibrating in any sense. So a fundamental, absolutely fundamental postulate of what we call statistical physics is that if you have two states, two quantum states, and they have the exact same energy, then they have equal probabilities of being occupied. And let's see, an example of this is, imagine a system that can isomerize. So I've got a sort of a W well here, and I've got a trans-type isomer on the left-hand side, a cis-type isomer on the right-hand side, and for the sake of argument, let's say that the energies of those two isomers are identical. The formation enthalpies are the same. So in that case, if I have Avogadro's number, a mole of these things, this is saying that I'm going to find half of them, 50% of Avogadro's number, in the trans conformation, and 50% in cis. And actually that probability holds kind of no matter what, but it's easiest to envision in a situation where it's easy to get back and forth. So if that barrier in the little W potential I drew is quite small, then we know that the system can slosh back and forth. The rotation isn't very hindered from the cis to trans, and it's easy to get there. But actually, statistically, you get there anyway. And for example, that's why you find in chiral systems, if you do synthesis without any particular care, you're going to wind up with a racemic mixture of different chiralities in the synthetic system, even though you can't take one conformer and just transform it into the other easily. As long as you get there in a statistical way, you're going to have this sort of 50-50 racemic mixture if you have the same energies. So that's a really, really fundamental basis for everything here. Now it turns out, and actually you can derive it from that by putting this thing in a heat bath, that if two states have different energies, and let's call that energy difference delta E, then the relative probability of those two states being occupied is given by this term. So the difference in probability is going to be an exponential, and it goes like e to the minus the energy difference of the two states divided by kt, where k, or k sub bt, is the Boltzmann constant. And this whole term, e to the minus delta e over kt, which we see all over the place, we call that the Boltzmann factor. So that Boltzmann factor determines the relative probability that two states with different energies are going to be occupied. And you can see that if the energy delta E is 0, then the relative probability is 1. So in other words, each state has the same probability of being occupied. So the fundamental basis is still in place there. And so if we put this in wave number form, this boils down to the difference, the relative probability of two states being occupied is equal to e to the minus 1.44 times the wave number difference in those two states, when we use wave number energy, so delta nu 1, 2, divided by temperature. And the 1.44 has units of Kelvin over wave numbers, because that cancels out the temperature and the wave number difference, and everything in an exponential has to be unitless, so that works out quite nicely. Now to scale this out, you can see that if I take 300 Kelvin and divide it by 1.44, I get about 208. I get exactly 208 wave numbers, which is really, really close to 200 wave numbers. So this is an exceptionally important thing to remember and take note of, that this kind of scale energy at room temperature is about 200 wave numbers. Broadly, what that says is that states that have an energy less than of order a couple of hundred wave numbers have a very good chance of being occupied, assuming we're taking as our reference the lowest energy state in the whole system, and we're going to set that equal to 0 in general. So any state with a few hundred wave numbers of energy or less is going to have a pretty good shot of being occupied. Conversely, states with more than a few hundred wave numbers of energy, their probability of being occupied rapidly and exponentially diminishes. And so that scaling is fantastically important. And you can also see that as temperature goes down, the states that have the gusto, that have the ability to be occupied, also go down. So at very, very low temperature, basically, only the very lowest energy states get occupied. At extremely high temperature, conversely, you're going to have lots and lots and lots of states that have almost the same probability of being occupied. Now let's take a very, very specific example of this, and we're going to use a system that looks a lot like rotation. So let's have a ground state, which we're going to put at 0 wave numbers, and again, we can always do that basically as a reference. It turns out all the math here is going to be independent of what that ground state energy actually is, which is kind of nice, and I'll leave that as an exercise to you to work out if you want to. But it makes everything easier to kind of think about if we just assign that lowest energy state an energy of 0. Then, so I got one of them, and then I'm going to put 3 states up here at about 100 wave numbers. And 1 to 3, etc. ought to be sort of a familiar looking thing. So the degeneracy of those states up at 100 wave numbers, that's what we call an energy level at 100 wave numbers, and the degeneracy is 3. There's 3 of them. Whereas the degeneracy G of the ground state there, that ground energy level, that's just one of it. So the degeneracy G is 1. Now what Boltzmann tells us, let's say we're at 300 degrees Kelvin, Boltzmann says the relative probability of this ground state is 1. So it's got an energy of 0, e to the minus 1.44 times 0 over t is equal to 1, and so its relative probability is 1. We go up 100 wave numbers, and those relative probabilities wind up being 0.62. E to the minus 1.44 times 100 divided by 300 is 0.62. But that's for each state. So it's 0.62 each. We have to multiply by 3, and that gets us 1.86. So the relative probability that one of the 3 states is going to be occupied up at 100 wave numbers is 1.86, actually more than the relative probability that the ground state is going to be occupied. It's impossible for me to stress how important this is. It's the fact that there's more states up here at higher energy means that I will tend to find interesting things happening in the world. If that weren't true, then everything would just sort of fall down into the lowest energy state. I mean, this is why molecules dissociate. This is why basically chemistry happens. It is entropy. So even though these things are higher in energy, because there's more states, they are also higher in entropy. And actually we're getting extremely close to the exact definition of entropy at this point. We're not going to get there. We'll leave that for next semester, but we're getting really, really close. So this thing, we call it a partition function, is the sum of all those probabilities. And it's 2.86 in this simple example, because I haven't given any higher energy states to worry about. It's just the 1 plus 3 times 0.62. So our total, what we call partition function, we call that capital Q, is 2.86. Now in the partition function, you can think of it as essentially basically how many effective states there are in the system. And so now when we add this up, and this is saying there's a little less than 3 effective states in the system. The ground state has a probability of being occupied of 0.35 because we take 1 over 2.86 to get that. Each of the excited states, the 100 wave number states, are going to have a probability of 0.62 divided by 2.86, and that's 0.22. 0.22, 0.22. So each of those 3 excited states has an equal probability of 22% of being occupied. And they're all the same, and that's that basic fundamental Boltzmann hypothesis that any state of the same energy has the same probability of being occupied. And so if I have a mole of these things here, and this is rotation we're looking at, so if I have a mole of these things, 0.35 of a mole are going to be not rotating at all, and the residue, which is about 0.66, it better be 0.65 if it actually adds up, but we have some rounding error. So 65% or 66% are going to be rotating a little bit with 100 wave numbers worth of energy, and those 3 states correspond to the orientation. So 22% are going to be rotating with the axis of rotation pointing up. 22% are going to be rotating with the axis of rotation in the xy plane, and 22% are going to be rotating with the axis of rotation pointing down. Those are the 3 different m sub z values for L equals 1. The m sub z would be -1, 0, and 1, and it plays out. So 66%, 65% are going to be rotating with 1 unit of rotational energy. 35% are going to be not rotating at all, and it all works out. We get 100% within rounding error of the molecules. We've described everything they're going to do. Now, again, I need to stress 0 wave numbers and 100 wave numbers here. The total, including that degeneracy, those are the energy levels, and these individual states are the individual lines I've drawn here. So the probability that any given state is occupied in general is given by 1 over this partition function times e to the minus 1.44 times the wave number energy of that state divided by temperature. The probability that any level is going to be occupied is given by the degeneracy of that level divided by the partition function times e to the minus 1.44 times the wave number energy of that level divided by temperature. And the partition function itself is the sum over all of the states of e to the minus 1.44 times the energy and wave numbers of that state divided by temperature, or it's equal to the sum over all the levels of the degeneracy of the level, e to the minus 1.44 times the wave number energy of the level divided by the temperature. Those are the same thing, but you have to keep very, very careful track of whether you're talking about energy levels or energy states. And so the formulas apply either way, and it all works out. But you have to keep that closely in mind. Is it levels or states? And the fact that the degeneracy of levels tends to rise as you go into higher energy, just like we looked at for that 3-dimensional particle in the box example, is fundamentally and just seriously important to the way chemistry plays out. How this all affects the way that rotational spectra look is actually pretty straightforward. So we've got our rotational energy levels. Remember, that's equal to the frequency, the wave number energy levels equal to the B constant times L plus 1, the rotational quantum number. The degeneracy of those levels, G of L, is equal to 2L plus 1. There's L with a negative m sub z, there's 0, and there's L with a positive m sub z, and so that's 2L plus 1. And the quantum number can be 1, 2, 3, etc., the principal quantum number L. So those are our energy level expressions, and the probability that the level will be occupied is equal to the degeneracy, 2L plus 1, divided by Q, times e to the minus 1.44 times B, the rotational constant, times L plus 1, divided by the temperature. And this gives us the probability, this is the probability that the initial will be in the initial level, okay? Because remember, if we're dealing with absorption spectroscopy, in order to get a photon absorbed, the molecule has to be in that initial state. So for example, if I'm going to go from 0 to 1, which is the first line that I can see, I need a molecule that's actually not rotating. I need a molecule that has a quantum number that's occupying that state with the quantum number 0, and so it doesn't have any rotational energy, and then I can goose it from 0 to 1 by absorbing a photon. If there are very few molecules in that condition, then I'm not going to get much absorption of light. There are always going to be some in the ground state, of course. Imagine I had if I'm interested in the quantum number 100, and the B value is something like 10. Well, let's see, 100 times 101 is 10 to the 4. So 10,100 times 10 is 100,000, 101,000 wave numbers would be the energy level of that thing. And at any reasonable temperature, the probability of that it being occupied is 0. There just aren't going to be molecules with a B value of 10 in principal quantum number L equals 100 at 300 degrees Kelvin. The probability is flat out 0. We're not going to find those, and so I'm not going to have any molecules actually going from L equals 100 to L equals 101 because there's no molecules in that rotational quantum state in the first place. So that's where the probability comes in. That's going to influence the intensity of the lines. Now the important thing is this 2L plus 1 term obviously increases rather dramatically, in fact linearly, as L rises. So L goes up, 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 and that's saying, ooh, 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 I've got more states. That's the degeneracy going up. That's basically entropy going up. But then this Boltzmann term says, hang on there. I am going to decrease exponentially, and in fact I go like L squared. So as the quantum number rises, that second Boltzmann term is going down towards 0 quite quickly. As long as the energy, as long as B times L plus 1 is significantly less than 1.44 divided by temperature. So basically, as long at 300 degrees Kelvin, as long as the energy of that initial state is significantly below 200 wave numbers, then the relative probability of finding a molecule in that a given state is going to be quite high. But once you get above 200 wave numbers, that exponential starts to really bite in and drop the probability dramatically. So now we can make an axis. We're going to actually label the y-axis now, and let's just use this cross-section sigma, which is going to give us the intensity of the absorption, how strong or weak those lines are. And then here we have the wave number of the photon, and remember that's equal to the wave number difference between the final and initial states the state that the system starts in, the rotational quantum number of the initial state, and then the rotational quantum number of the final state. And again, for rotations, the difference has to be 1. So we go from L to L plus 1. And now we're going to have lines, and they're going to go up and down. They're going to go up at the beginning because the degeneracy is rising, but then once the energy of the initial state gets above 200 or so wave numbers, they're going to go back down. And so that's basically what explains this rising and falling behavior of the rotational spectra. And again, these represent the transitions from L equals 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, etc. So each of them is making a change of 1 in the quantum number, and the spacing is even. So the spacing is always twice the rotational constant, 2b. And that's it. That explains everything there is basically to know about the rotational spectra. There's just a couple of very small details, but pretty much that tells you what these things are going to look like. They're evenly spaced. The spacing is twice the rotational constant b. You go from initial quantum number L to final quantum number L plus 1 in absorption mode. The intensity rises, the cross-section rises, while the initial energy level is significantly below 200 wave numbers at 300 Kelvin at room temperature. And then as you go to higher and higher initial quantum numbers, the occupancy drops very, very rapidly due to that exponential, and so the cross-section the strength of those lines drops off as well. And that's it. That explains everything you need to know about what a rotational spectrum looks like.